Hello, everyone. My name is Shaun Clarke. I'm here to continue yesterday's discussion on Monte Carlo transport and techniques for nuclear engineering applications. This will be a continuation of yesterday's lecture, so if you missed yesterday, you can find that one on the website to catch up. But for now, I'm going to start directly where we left off on yesterday. So we're going to be talking about Monte Carlo transport and the ways that we can apply it to nuclear engineering applications. Yesterday, we did a lot of background and talked about the theory of Monte Carlo and why it's applied, and went through some basic examples to illustrate Monte Carlo principles and how they can be used in various applications. So today, we're really going to focus on radiation transport, and we're going to walk through the various steps of a transport problem and discuss how we can use Monte Carlo to sample the various particle properties along the way. So with that, this slide describes the problem that we're going to be considering today. So we're going to consider a particle source, maybe it's neutrons, incident on a slab, and the particles are going to be incident with some angle, theta. We're going to consider this slab to be infinite in all directions except for this one direction. So it's like a one-dimensional slab. And we're going to consider that particles can interact in this slab in two ways. They can either scatter or they can be absorbed. And then we'll talk about what all that means. We're going to assume scattering is isotropic in the lab system. And what this means is when a particle undergoes a scattering collision, any angle is equally probable for the outgoing angle, and that'll just simplify the random sampling that we're going to be talking about today. We're also going to make the assumption that once these particles scatter, they do not lose or gain energy, which is not a good assumption in reality. But in this case, again, what it'll do is allow us to really just focus on the random sampling piece and not worry so much about the details of the physics. So we're going to assume kind of an ideal scatter in which particles don't lose any energy. And what we're going to be trying to do is to determine the probability that particles transmit through the slab so that they can make it all the way through, the probability that the particles get absorbed in the slab, or the probability that the particles reflect from the slab, meaning that they scatter and leave the slab through the same surface by which they entered. So this graphic just shows a visualization of what we are talking about here. So transmission through the slab is one possible fate of the particle. That's shown by the green track there on the right. So the particles maybe scatter around a few times and eventually find their way out the back end of the slab. The red track, it would be an example of a particle being absorbed in the slab. So the particle track terminates before it exits the slab, and it terminates by absorption on one of the nuclei in the slab. And the blue track shows the third possibility, which is reflection from the slab. So as I said, that's the case in which a particle bounces around and leaves the slab through the same surface at which it entered. So before we start, I need to go through a few definitions. So the first definition that I want to talk about was something called the random walk. A random walk is a phrase that's used in particle transport. It's a phrase that's used specifically in Monte Carlo transport to describe the history that a particle takes in its transport. History meaning all of the various collisions and things that happen throughout the particle's lifetime. It's called a random walk because at every step of the way, every property of the particle is random, and we'll show why that is here in the next few slides. But we can think of the random walk as, of course, this collection of path lengths and things that's kind of shown here on the left-hand plot. But really, what it is, it's a set of variables. So you can think of each point in the particle's lifetime as a collection of variables. In this case, we have the variable r, which is the three-dimensional position, the variable e, which is the particle's energy, the variable omega, which is the direction of particles travel. And we can save these state variables at any and every position along the particle's track throughout the particle's lifetime. And that collection of variables essentially is the random walk. Imagine if you had all this data in front of you you could use those data to actually recreate this particle track. And that's really what we do in Monte Carlo transport, is we store those random variables throughout the particle's life and use it to, do whatever calculation we're trying to do, whether it's computing a flux or computing a dose or detector response, whatever. This collection of data, these random walk variables, allow us to do that. So when we say random walk, that's what we're going to be meaning. The other definition, which I'm sure most of you are familiar with, is this idea of solid angle. We're going to use the variable omega, the bolded omega here, to be a direction vector, which is a function of two other variables, azimuthal and polar angle, theta and phi. So when we say omega here, we're going to be talking about a direction for the purposes of today's discussion. So in Monte Carlo, to generate a random walk, again, why is it called a random walk? Well, at the beginning of the particle's life, the position that it's born, its energy, its initial direction, all of those things are random. They're random because generally speaking, we're talking about radiation. And radiation sources, radioactive decay, all these things are by nature random processes. So even at the beginning of its life, the particle's properties are born with some random distribution. The distance that a particle takes between collisions is also random, and that's just due to the probabilistic nature of neutron, in this case, interactions inside a medium. We can't actually predict how far a particle will travel between one collision and the next. We can produce a distribution, and we can sample from that distribution, but we can't actually say with any certainty what the exact distance will be. That distance is random. If the collision is scattering, the direction that the particle will go following that scattering interaction is also random. In real life, it depends on the energy. Of course, for today, we're going to ignore the energy piece of it, but the direction and energy are both random and they need to be sampled. If the collision is absorption, that reaction may produce secondary particles. Sometimes, neutrons get captured and produce gammas. We can have a fission reaction occur, which will produce many secondary particles. Whether or not those particles emerge in the first place, and if they do, what are their properties? All of those things are random and need to be sampled using Monte Carlo random sampling. So the collection of all of these things can lead to the particle's life terminating. It can terminate through a variety of processes. We talked about a few of them already: absorption, leakage, meaning it just leaves the problem boundary. Perhaps the particle energy has fallen below some range of interest. All these things are criteria that are used in Monte Carlo transport to terminate a particle track. So the question is, how can we actually go about simulating these processes? So there's 6 fundamental parameters of a particle when it's emitted from the source. Typically, we consider a 3-dimensional problem. So your spatial position has 3 parameters, X, Y, Z. The direction is going to consist of 2 more variables, theta and phi, and 1 energy parameter, scalar energy parameter. So when we're going to create a particle source, we need to define all of these parameters. And some of them may be fixed. If the radiation that you're simulating has a fixed energy, that's an easy one. But if the properties are not fixed, we need to define our distributions to sample them randomly. And what we typically do in Monte Carlo is we sort of make this assumption that all 3 of these properties, position, direction, energy, are separable, meaning we can sample them independently of one another and put them together, and that will produce the properties of our source. In general, the particle source needs to be normalized, meaning it has to be emitted with some energy, it has to be emitted in some direction, and has to be emitted at some position. So all of these individual distributions must integrate to one. So just an example to talk about position. So obviously, if your Monte Carlo transport is starting with a point source, that's easy because the point source is just fixed at a certain position, so there's no random sampling needed. The source can be considered to be born always at the same position. However, position can also be a random variable. So the example here on the slide is one of a source where the position is distributed along a line. And you can see the graphic here on the right where we want the source to be born at some position along this line between R1 and R2. These R1 and R2 are three-dimensional variables, so this line is existing somewhere in the three-dimensional coordinates of our problem. So this is similar to the example we did yesterday of sampling in the box. In this case, we're sampling along a line, so the distribution of the source along DL has to normalize to 1. So we end up with a 1 over LDL, where L is the length of the line. And at that point, you just do the simple integral down here at the bottom. This is our inverse transform method, where we're taking our P of L dl, integrating it from 0 to L, and setting that equal to the random variable C. Rearranging, we get our position L to be equal to the random variable times the overall length of our line. And then the length of our line is just calculated in this way for an arbitrary three-dimensional line. So if you had a situation where your particle source was born uniformly along a straight line, this would be the approach one would use to sample randomly where along this line from R1 to R2 the source position is located. That's kind of a one-dimensional approach. You can also have a situation where the particle is born in area. So maybe you have a rectangular area source. In this case, this is exactly like the example we did yesterday of the hit or miss problem, where we want to sample uniformly positions inside of this green rectangle. In this case, our green rectangle goes from 0 to A in the X direction, 0 to B in the Y direction. So the sampling is quite trivial. We write it out here rigorously, but the X coordinate is just a random number C times A. Because the random number is distributed between 0 and 1, the distribution of X is between 0 and A. So it's quite straightforward. Same thing for B. The B coordinate, Y coordinate is B times the second random number, eta. So in this case, eta and C are two random numbers that are sampled individually. They're independent of one another. And by doing that, we would produce a distribution of points that are uniformly distributed all along this area of AB. The source particle energy. We're not going to spend too much time on this one today because we're going to ignore it for the purposes of our scattering, but just wanted to say a few words about source particle energy and the ways that it can be sampled. So the first one, and most straightforward, is a situation in which you're simulating a monoenergetic source, meaning the source emission has a single energy. So in that case, there's no random sampling required. The source particle is just defined to have that energy upon birth. Second example will be a gamma ray source that emits multiple photons at different discrete energies and different intensities. So in this case, you would provide the code of the transport. Would begin by just sampling those two different energies. So if you had E1 and E2 that are equally probable, you would essentially flip a coin between those two energies, and that would define the energy at which the source particles are born. The last one, and probably the most common, is some type of continuous spectrum. So if you think of like a Watt fission spectrum or a Maxwellian thermal energy spectrum, these are just two examples of common continuous distributions that are used in nuclear engineering. These distributions are all well known mathematically, and you can write expressions to sample randomly from them and define the particle energy that way. Okay, so the direction. So we have our particle source. It's born at a certain position. Maybe it's along a line, maybe it's in an area, maybe it's at a point. Once we've chosen that position randomly, we're going to choose the direction. So in this case, our direction is defined as this omega variable, which depends on two different angles. It depends on the polar angle and the azimuthal angle. And because we need a probability distribution function to do the sampling, the first thing we have to do is normalize that PDF. So our PDF is this P of omega d omega. is some constant times d omega. This constant is our normalization factor. Okay, in order for this p of omega to be a PDF, this function needs to be normalized. So we just set it equal to 1, do the integral, and we know that solid angle integrated over all space is 4 pi. So our constant works out to 1 over 4 pi to ensure that this PDF integrates to 1 over all space. So the next thing we need to do is the inverse transform integration of this PDF. So to make it a little more straightforward, what we do is we break our d omega into the two different angles there. So it's our polar angle theta, our azimuthal angle phi, and we can write d omega as sine theta, d phi, and the 4 pi stays. And then we break it into two parts that are just convenient for our integration. So sine theta d phi over 4 pi is equal to sine theta d theta over 2, and then d phi over 2 pi. And then we can make the assumption that these two angles are independent. So we can assume that for any particle direction, the polar angle is independent of the azimuthal angle. And then we can do the integrals independently. So they're all written out here. So if our P1 is our theta distribution, commonly in Monte Carlo calculations, we don't use theta directly, we use cosine of theta. It's just a convenient value to use in the transport. So if we change the variables from theta to mu, where mu is cosine theta, we can do this integral. And then we can set P2 equal to the second part, which is the d phi over 2 pi. So the integrals are written out down here, but basically we're doing each integral independently, setting it equal to random number, and then solving for the dependent variables. So in this case, our mu variable, our cosine of theta, is equal to 2 times a random number minus 1. So this is our first direction. Our second direction, the phi variable, do the integral, set it equal to random number, solve for phi, and that second angle phi is equal to 2 pi times our second random number. So by sampling two random numbers, two independent random numbers, we can sample values for both mu, which is cosine theta, and the angle phi. Once we have these polar and azimuthal angles sampled, we can define our direction vector as a function of those two angles, theta and phi. Okay, so we've talked about particle position, we've talked briefly about particle energy, we've talked about particle direction. So now we have a source particle that's been emitted from the source at a certain position in a given direction with a certain energy. So the next question is, once the particle enters the slab, how far will it travel? And this is how we do that. So in this case, our PDF is e to the minus sigma r, where r is the direction or the dimension, length dimension, and sigma is the total cross section. So in our case, the sigma would be sigma scatter plus sigma absorption. And we can set up our inverse transform integral as usual. So again, little p of x is our PDF. Big P of x, or r in this case, is our CDF. We integrate from 0 to r, e to the minus sigma r prime, sigma dr prime. Solve that integral as 1 minus e to the sigma r. Set it equal to random number down here. So this is our integrated CDF. Set it equal to random number. Solve for r, which is the variable of interest, as r equals minus 1 over the total cross section times the log of 1 minus the random number. We can do a small simplification here because of the nature of our random numbers. If you remember from yesterday, these random numbers are defined as values between 0 and 1, uniformly distributed values between 0 and 1. So because of that property, 1 minus random number is the same, just distributed in the same way as random number. They're numerically different, but the distribution is the same. So we can just replace it and make the arithmetic a little simpler as we apply this in a code. So the distance, the particle will travel between collisions is equal to 1 minus sigma, -1, times the log of random number. This random number, again, is a number less than 1. That's why this negative sign is here. So the positive, the direction will come out positive after we do this random sampling. Just as an aside, in the problem we're talking about today, the slab is all one material, but you can have a situation in real life or in real application where you have multiple materials next to each other that are different, have different cross sections. So you can combine them just like this, where if you sample this distance and that distance leaves the slab, you would then sample a new distance in the next slab with the new cross section. So you can just stack these as needed if you're transporting particles through regions that have multiple cross sections or multiple material types. Okay, so the particle has been emitted in a direction with an energy. It traveled some distance into our slab before its next collision. So now we have to ask the question, what type of collision happens in that slab? So the collision type is sampled using the cross-section data. This slide shows a general form. So the total cross-section, we're talking about neutron cross-section here, is equal to the sum of all of the partial cross-sections. So you can have elastic scatter, inelastic scatter, radiative capture, fission, maybe it's N alpha, NP reactions, N2N. There's a whole litany of reactions that neutrons can have in these various materials. And if you add all those different possible cross sections up, you get the total cross section. And this is an example of a discrete PDF. So it's not unlike rolling up a six-sided die like we talked about yesterday. Only in this case, the die has many more than 6 sides and the faces are not equally probable. But in principle, it's the same thing. It's a discrete PDF. So we need to normalize the discrete PDF. So we just divide the entire expression here by the total cross section. So sigma total over sigma total becomes 1, and each of these cross sections on the right then becomes a partial cross section. They're each divided by their total. And we can define this as essentially the sum of the probability of a given interaction type X. So in this notation, this little X can be, gamma 2N or gamma or fission. This is the probability of each individual reaction type occurring. So once we have this normalized discrete PDF, we can create kind of like a step function, exactly like we talked about yesterday with the dice example. So it looks kind of like this. This is a simplification of just the first few reaction types, but this is the probability here on the y-axis. So the first P of NN reaction is just PN. Make a CDF out of that. So the probability of PN or PN prime occurring is the sum of those two partials. The probability of PN, PN prime, or P gamma is the sum of those 3 partials, and you would just keep going up and up and up until you've added up all of the possible reaction modes. And if we set that y-axis equal to a random number, we can then sample the random number, find out which band it lands in, and that's how we sample the reaction. So if we sampled a random number that landed here, then that would tell us, okay, in this case, we had a P gamma and gamma reaction occurring. The same exact approach that we used to sample the six-sided die rolls yesterday. Okay, so the particles traveled the distance, it's had some collisions. Because in our simple problem, we're only considering 2 possible collision types. We're only considering scatter or absorption. If the particle is absorbed, then that terminates that particle's life. So we can then score it as an absorption reaction. If the particle scatters, we have to compute its direction when it leaves that scatter. In this case, because we assumed that all scattering is isotropic, in our problem statement, we can use the same exact random sampling approach to sample the isotropic direction that we used when the particle was born. So the particle travels some distance. We do our random sampling and we discover that it was a scattering reaction. So then we sample our direction, leaving that reaction. then we would sample a new distance, sample a new reaction type. If it's scattering, sample a new direction, so on and so forth, until the particle either leaves the slab through reflection or transmission, or is absorbed. Continue this process until the particle is finished, and then you would start a new particle, and that's how the Monte Carlo transport could proceed to solve this problem. Okay, I want to talk a little bit about scoring and how we can estimate the various quantities in Monte Carlo transport, but I'm just going to check the chat real quick, see if there's any questions here. If you do have questions, please feel free to type them. We will have some time at the end for questions as well. I've got about maybe 8 or 10 more slides here, so we can take questions at the end as well. Okay, so Monte Carlo transport, once we do this transport where we have these particles, they've scattered around, they've been absorbed, how do we actually estimate the quantities that are of interest to us in nuclear engineering? So particle flux, reaction rate, dose, things like that. How are particle histories related to these reaction rates? So if you take a step back and think about a real experiment, how would we do this in real life? If we could zoom in, inside of this this container, and we could look at the particle behavior in a certain region, maybe call it region D. We could take a look at the particles that are traveling in there. If we could imagine being able to see that with our mind's eye, and we could just count them. We could count the number of particle tracks or count the number of collisions that are happening in our detector cell. And that's how we could do it in real life. In fact, radiation detectors actually do that. They're giving us a measurement of the particle behavior in a certain region. In Monte Carlo, we can essentially do the same thing. As we discussed yesterday, one of the advantages of Monte Carlo is it can really give us an analog to the true physics happening in the real experiment. So we can set up these detector regions in our Monte Carlo transport, and we can estimate flux reaction rates in much the same way we would imagine doing them in a real experiment. There's a few different scoring methods. It's called scoring in Monte Carlo because you're literally counting the number of times that these things happen. There's 3 primary approaches that are used in most kind of commercial Monte Carlo codes: collision density scoring, track length scoring, and plane crossing scoring. And I'm going to give you an example of each of those here. But before that, I just want to say a quick word about the quantities that we're interested in here. So if the big picture, the kind of holy grail, if we knew this, we'd know everything, is angular flux. Angular flux is the particle population as a function of position, energy, and direction. And if we knew that all throughout the problem, we would know everything. Typically, when we're doing Monte Carlo estimation, we're scoring some component of that. So you talk about flux, maybe we're just going to integrate our angular flux over all angles and over energy, for example. And that would give the scalar quantity flux as a function of position. Sometimes we're interested in current, which is similar to flux, but in this case, it's directional. So it's looking at how particles are traveling across certain surfaces. And the Monte Carlo estimation, because it's like track by track, we can do these integrations numerically as the particles are being transported through the geometry. So for example, these are the things that are commonly estimated in Monte Carlo calculations. So if you're running any sort of commercial Monte Carlo code, that code is going to have mechanisms built in to tally these various things. Some codes use the name tally, some codes call them estimators. That's just the Monte Carlo jargon for computing what you want to compute. Current tallies in Monte Carlo are typically scored using a surface crossing estimator, so you're going to be counting particle tracks crossing a surface. Flux tallies in Monte Carlo are generally integrated over space, so those are going to use a track length or collision estimators, and I'll talk about this in the next slide. Reaction rates are things that are also tallied in Monte Carlo codes quite often. Reaction rate is essentially the flux times the cross section. So reaction rate tallies are essentially a subset of flux tallies. If you know the flux and you know the cross section, you can compute the reaction rate. Same thing with dose, energy deposition. Those are also kind of a subset of flux tallies. If you know the particle flux in a given region and you know the energy of those particles, you can then compute the dose using the cross section or energy deposition type modifiers to go from flux to dose. So how does it work? So here's an example of what a surface crossing estimator looks like. So in this case, let's consider this surface over here, delta S, and what we want to know is how many particles are crossing that surface. So in the Monte Carlo, in the sampling, what's done is during the transport, the code is literally counting up the number of tracks that cross that surface, delta S. Keeps track of the angle. Sometimes the codes will score up by the angle, but in general, what we're doing is counting the number of tracks that cross that surface. And then the estimator works like this. So we're adding up 1 every time a particle track crosses. We count 1, we divide by the surface area, we divide by the total number of histories, and there's also a correction that's done for particle weight. So we mentioned this very briefly on Tuesday, but particle weight is a quantity that's used in Monte Carlo to keep track of the statistical contribution that a particle track has to the solution. So in general, particles are born with weight 1, and if there's no statistical biasing happening anywhere in the problem, the particle's weight will stay 1 for its entire life. Some Monte Carlo codes allow the users to intentionally bias their solution and then change the weight accordingly to ensure that the final solution is unbiased. And so when that happens, when a particle track is scored, it's scored by its weight, and that contributes to the tally. So the particle weight at the time of the scoring is this W sub I. The particle's weight when it's born is this W sub 0. If the transport is fully analog, these are both just 1, and it literally just becomes 1 over the surface area and the number of particles every time a track scores. So this is just counting up the number of tracks that cross the surface. Because we also tally the angle, we can look at, J plus, J minus, so particles going in or coming out of a given surface is also something that gets commonly scored in Monte Carlo. For particle flux, in this case, we're generally doing particle flux estimation in a volume. So in this tally or estimator, there's 2 ways to do that. There's track length scoring and there's collision scoring. Track length scoring is the most common. So in this approach, we have this volume. The circle here is the volume inside of which we're interested in tallying flux, and here is the recipe, and this recipe gets applied for every particle track, every history in the problem, where the approach is to take a sum of the distance, d sub I is the distance that each track spends in this volume. And we also take note of the weight. So again, if the simulation's analog, W0 and WI will both be 1, so they essentially cancel. And the track length flux estimator becomes a sum of the track lengths, all the track lengths for that history in the given cell, divided by the volume of that cell, and divided by the number of source particles. So the units here, track length has units of length, volume has units of cubic length, cubic centimeters. So the units here are 1 over area, or 1 over centimeter squared, for example, which give you the units of flux. In Monte Carlo, we're always dividing by the number of source particles because what we're trying to do is estimate probabilities based on a large number of statistical trials. Estimators in all Monte Carlo codes are divided by the number of trials or the number of particles sampled. Collision scoring is similar. There just is a divisor by the total cross section to make the units work out. So in this case, instead of counting the length of the track, we're actually counting the number of individual collisions that happen in the cell. And the 1 over cross section fixes the units so that we still end up with 1 over area for the units. So in principle, the track length estimation, collision estimation, both result in the same value for flux. However, there's advantages and disadvantages to both. So the track length estimate is generally better if you're thinking of a volume that's relatively thin. So any kind of volume where collisions are unlikely, right? So if collisions are unlikely, if there's no collisions, the collision estimator returns 0. But the track length estimator will not return 0, because even if there's no collision, there's still going to be a track length as the particle passes through the volume. So in most Monte Carlo codes, I think the track length estimator is kind of the default, just because it's a little bit more robust to thin volumes, but collision scoring is still equally viable, assuming the volume is large enough that enough collisions take place to build up those statistics. Okay, so I've kind of touched on this a little bit, but I just want to mention it again here because it is relevant. So this analog versus weighted Monte Carlo. So when we say analog Monte Carlo, what do we mean? Analog Monte Carlo essentially means the particles are born with weight 1, and the weight never changes from 1. So there's no alteration of the PDFs. There's no biasing taking place in the calculation. There's no variance reduction taking place in the calculation. Variance reduction is a name for a class of techniques where the user intentionally biases the PDFs along the transport to increase particle population, but then the weights have to be adjusted to ensure that the solution is not biased. But in analog Monte Carlo, we're not doing any of that. In analog Monte Carlo, every track that gets simulated in the transport is analogous to a real particle. So everything is weight 1. In this case, we score 1 for all tallies of interest. So that W sub I that we just saw on all the previous slides, that's just 1. So we're always scoring 1. In weighted Monte Carlo, or when variance reduction is applied, the user, again, can alter the PDFs to favor events of interest. So if you're really interested in looking at, I don't know, particles in a certain region of the problem, you can do splitting to force particles to go in those directions, for example. And this biasing is often not physical. So the particle's weight needs to be adjusted so that the solution at the end is not biased. So the most common example of this is an approach called an implicit capture, where in particle transport, when neutrons get captured through a capture reaction, they cease to exist in the transport. But what you can do in Monte Carlo world is you can actually keep the particles around. That's what this bullet says here. Particles can survive collisions they normally wouldn't survive. So you can have capture events that actually produce neutrons, but as long as those neutrons have a reduced weight, they can still contribute statistically to the tallies, but they won't change the overall mean of the capture rate. That's an example of kind of weighted Monte Carlo. But when this is done, it's important that when the weights are changing in the transport, that anytime there's an estimator or a tally being applied, those particle weights get scored rather than blindly scoring 1 for each occurrence. So a weighted Monte Carlo typically is, quote unquote, better. It can provide you, increased statistics in the regions of interest, whether it's regions of space or energy or time. It allows for more efficient simulation. However, analog Monte Carlo is also nice because you can believe that every particle track really is, corresponding to a realistic individual particle. Okay, so in summary, the life of particles is random. So we've talked about this a lot over the last couple of days, but basically, whenever a particle is born, its location, direction, energy, it's all random. Distance traveled between collisions, random. Collision is scattering, the direction, energy, they're also random. If the collision is absorption, the particles that emerge and their properties are also random. And the process by which a particle life terminates is also random because of all these other behaviors. So this random nature of radiation and radiation transport is what makes the Monte Carlo method really well suited to handle these types of calculations. So why use Monte Carlo? Again, it's got a number of advantages, and the first of which being it can represent geometrical complexity of systems as they exist. So in other approaches such as deterministic transport or other things, there's often homogenization, whether it's in space or in energy, that's required, where the user has to simplify the geometry so that the transport method can then handle it. In Monte Carlo, we're typically using combinatorial geometry to build a geometry, and it's using pointwise cross-section data over the entire energy range. It can serve as an efficient numerical integration method for multidimensional problems. Again, because it's all pointwise, there's no homogenization required. We can use it to solve very complex multidimensional problems. Because the particle transport in Monte Carlo can be seen as the analog of true particle transport, it can often be used as a benchmark for other deterministic methods when real experimental data are not present. So with that, I have a couple references here for some of the textbooks and things where the material was pulled from. And with that, I would stop and ask if there are any questions. So the question here in the chat, in calculation, which of the two, analog or weighted, takes more time? That's a very good question. Generally speaking, weighted Monte Carlo takes more time. And the reason for that is, generally speaking, when the user is biasing the transport, they're biasing in a way to increase particle population in the regions where they're tallying. So because of that, the calculation can take more time per history to run. So for any given history, it takes more time. However, the tracks that you're transporting are generally more valuable to your solution. So each history takes longer, but each history also contributes more to your solution. So in general, you come out ahead with weighted Monte Carlo if the weighting or biasing is applied in an efficient manner. Let's see, I'm just scrolling up to make sure there's no other questions. Okay, I don't see any more up there. Normally when the geometry is too complex, it takes more time to smooth the model. What would be the measure to reduce simulation time? Yeah, so you're correct. So I'm reading the second from the bottom question here. Complex geometries do take more time to simulate because in Monte Carlo, because we're transporting every particle track at every collision where we are sampling the distance that the particle travels, then the code has to figure out which cell the particle is located in so that it can grab the cross sections. So complex geometries do take more time in Monte Carlo, and there's really not a way to mitigate that other than not using more cells than you need to. So being judicious in the geometry that you're setting up and really making sure you're modeling only the portions of geometry that really contribute most to the tallies and quantities that you're interested in. Let's see. Yesterday, how to tell if a solution is statistically accurate? Yeah, so we talked a little bit about statistics yesterday, and I touched on it today. But essentially, in Monte Carlo, what you're doing is using these estimators that I talked about here at the end, and you're counting contributions to those estimators. So the quality of the statistical solution relies on having a large number of scores. what a large number means is not really, you can't really define that a priori. It depends on your problem and what you're actually simulating, but we can always say that the relative error on an estimator in Monte Carlo decreases as 1 over the square root of the number of scores. So if you consider a situation where the tally has 10,000 scores, that's going to be on the order of 1% uncertainty, right? So 1 over the square root of 10,000. So that's kind of a rule of thumb, but really to answer that question fully, you need to have some knowledge of the transport that you're actually performing. So you would look at a tally in a certain region, check the uncertainty, and then based on that uncertainty, you can say, okay, I ran this thing for 1 million histories and the uncertainty is 10%. So if you want to reduce that uncertainty down to 1%, you would need to run the problem 100 times longer. So from 10% down to 1%, and then squared, because it's 1 over root n. So you can always say how much longer you need to run a problem, but you can't really say a priori how long it needs to run to get, statistics of a certain level. Yeah, another question coming in Monte Carlo simulation, more particle histories. So if the geometry is complex, such as the full reactor core, how many particles should be used to get a statistically sound result? Again, very difficult question to answer, actually impossible question to answer a priori. The best approach here is to set up the model and just run it for a reasonable amount of time, and then check your tallies. So it depends if you're trying to tally, flux in a certain regions or radiation dose or whatever you're trying to tally. I mean, you can check those tally results and you can check their statistical uncertainty for a certain number of histories. And then based on that uncertainty, you can predict how much longer you need to run or how many more histories need to be run based on this 1 over root n scaling factor for the tally uncertainty. Okay, I don't see any more questions coming in. We're near the end of the time here. So I want to thank you again for coming for the second part of this lecture. And I'll encourage you to come again tomorrow. Tomorrow, we're going to have a guest speaker, Professor Chris Perfetti from New Mexico, to give us his perspective on Monte Carlo and deterministic transport and how they can be applied to nuclear engineering. So hopefully we'll see you all again tomorrow. Enjoy the rest of your day.